So RDT, or the Ross droplet technique, has been all over the news recently. It's not something new, it's been around for a pretty long time. And home baristas like you and I, we know if we spritz the bean with a bit of water, it makes these grinds a little bit more fluffier. To be honest, I've not used RDT for many years now. And this is because I found the results to be quite variable. Sometimes it worked, sometimes it didn't. But it is this paper by Professor Hendon which really sparked my interest. And it has been discussed extensively by Lance Hendrick and by James Hoffman. But is the hype really justified? Can we separate the chaff from the beans? So in this video, we shall look at some aspects of the Hendon study that are relevant. So I'm not going to go through the entire study. We'll just look at some specific elements. I will discuss my experiments and let you know what I think about RDT and how best it can be used. So what is triboelectrification? Tribo is simply the Greek term for rubbing. So triboelectrification is the electricity that you get when you rub two objects against each other. This is the same static electricity that you see when you comb your hair. So your comb will then get a charge and you can attract paper particles with it. As you can see, I have lost all ability for triboelectrification. So how does this actually occur? Now we don't exactly know how it occurs, but there are some theories. And one of the theories is that when two particles, they rub against each other, there is transfer of electrons. So the particle which gives up the electron, that becomes positively charged, and the particle that takes up the electron becomes negatively charged. What happens in a grinder? So in the grinder, coffee particles are rubbing against each other, they're rubbing against the burr, and this results in the formation of charged particles. Now triboelectrification is actually very common in the milling industry, and it is actually a problem because when you have a large milling process, it can generate dust clouds, and if these are charged, then there is a risk of an explosion. And there have been incidents where there have been casualties because of explosions. But don't worry, you're not going to get an explosion in your grinder. But triboelectrification does cause some problems. And the problems it typically causes are particles adhering to your coffee grinder and the formation of aggregates. Now what seems to happen is that fine particles, they charge differently to the bigger particles, which means they attract each other, forming clumps. And this clumping is very common in nature. Triboelectrification is the reason why you and I exist, because it was the mechanism by which the smaller dust particles in the early universe, they were attracted to each other, and then they started getting bigger and bigger, leading to the formation of planets. Another mechanism of charging is called as fractoelectrification, and this is what happens when objects fracture. So this is what happens to magma fragments as they come out from the volcano. Now, fractoelectrification is not restricted to just volcanoes. It can happen during fracturing of many different kinds of material, such as wood, ice, and of course coffee beans. So let's discuss the paper in some detail. So for this experiment, they used an EK43 grinder, and this has a 98mm burr. And what they did was they looked at the amount of charge in the grounds that were produced. So the question that they asked was there any correlation between the color of the roast, so whether it was light or dark, and the amount of charge? Now to quantify the roast color, they used something called as a spectrophotometer. This uses infrared light, and you can get a number called as the Actron number, which is a guide as to what the roast color is. So it is a way of standardizing the roast color. So typically a medium roast coffee will have an Actron number of anywhere between 50 and 55, a medium light between 60 and 65, and light is between 70 and 75. What they did next was plotted a graph. So on the x-axis you have the Actron color, on the y-axis you have the amount of charge, and they looked at whether there's any correlation. Now apologies if you know this already, but the way you look at correlation is you look at whether there is a constant relationship So when one value increases, does the other value increase? So every time the electron value increases, does the amount of charge increase? If there is an absolute correlation, what you will get is a straight line. If there is no relationship, then the values are all dotted around and you won't get a straight line. So this is what the authors found. Now the dotted line that you can see, it is called as the line of best fit. Now the authors state that there is a weak correlation between the roast color and the amount of charge. What they found was darker the roast, more the charge. You can see that the R-square value is 0.35, and for those of you who do not know what R-square value is, what it means is it gives us an idea of how much of the charge is explained by the roast color. So an R-square of 0.35 means that about 35% of all the variation in the charge can be explained by the roast color, and the 65% is because of something else. Now, although this is a weak correlation, it is still significant in my view. 35% is a fairly high number, considering that there might be so many other variables that might explain the charge. Now, there is another interesting feature that you need to consider. If you look at the data very carefully, you will see that beyond an electron value of about 70 or so, the charge is actually almost zero. So what this means that for darker roast, there is a clear correlation. So as the roast becomes darker, you get more charge. As the electron number goes beyond 70, the charge is actually almost zero. From this data, it is clear that the relationship is not linear. Now, the other aspect that they looked at is whether there's any correlation between moisture content and the total charge. Now, there is some correlation between the roast color and the moisture contents. So typically, lighter roasts, they will have a higher moisture content, and darker roasts will have a low moisture content. However, what they found is that it is possible to have a different moisture content. So you could have a dark roast which has been done really, really quickly, so the moisture content is higher, or you could have a lighter roast which has been done roasted much more slowly, which means it's going to have a lower moisture content. And what they found is that there is maybe a slightly better correlation between moisture content and the total charge. So the R-square value was about, I think, 0.41, which means 45% of all the variation can be explained by moisture content. So in their view, moisture content is a better predictor of total charge than your roast color. So now we know about the total charge of the grinds which are coming out. For the next part of the experiments, what the authors did was they decided to separate the particles out based on the charge. So for this part of the experiment, they used two plates, a positive and a negatively charged plate, which meant that as the particles were coming out from the chute, the negatively charged particles were attracted to the positive plate, and the positively charged particles were attracted to the negative plate, and the neutral particles fell straight down. And what they also did is they looked at the particle size distribution for the positive and the negatively charged particles. So what they found was that smaller particles, by small particles I mean fines, which is less than 100 microns in diameter, they tend to be mainly positively charged, but they could be both positive or negative. The larger particles, however, they're always negatively charged. It is the in-between range, the intermediate range, which determines the overall charge of the grinds. So as you can see here, lighter roasts tend to be slightly more positive. So you have both positive and negative particles, but there's slightly more positive particles. But if you look at the dark roasts, it's predominantly negatively charged particles. So remember, light roasts tend to be positively charged, dark roasts tend to be negatively charged. But what's not been discussed in this paper is what actually happens in the neutral bin. What is the particle size distribution of the grind particles in the neutral bin? Do you see more aggregates? Because one of the theories is that these positive and negatively charged particles, they bind to each other, which means the charge is neutralized. Is that what you see in the neutral bin? The paper does not discuss this. So what do we know so far? We know that medium to light roasts, they have less charge overall and tend to be positive or near neutral. Dark roasts tend to be negative. Now there is evidence from other research that negatively charged particles tend to foul more easily. By foul, I mean aggregate more easily. And this is a study which they were looking at the effect of different mixtures on instant kind of coffee, and what they found is that when the overall charge was more negative, so there were more negatively charged particles, they tended to aggregate more. So it makes intuitive sense that darker roast coffee, they're going to have more aggregation. Now in another part of the study, the authors looked at, okay, what happens when you actually start to grind finer and finer? And not surprisingly, the finer you grind the particles, the more they are charged. However, there's a lot of variability. What they found was that darker roasts, they're negatively charged, and as you keep grinding finer and finer, you get more and more charge. But there comes a point when actually the charge reduces. And what they think is happening is you're getting all of these negative charges, and they're binding to the positively charged particles, and so these charges are neutralized to an extent. With lighter roast coffee, when you go to the espresso range, you again see a lot of variability. Next, to differentiate between the effects of triboelectrification and fractoelectrification, the authors ground the coffee again, but this time at a very coarse setting. And what they found, that the charge did not increase. In fact, the charge was reduced by almost 90%. What this means is that it is the fracture of the coffee beans which is responsible for most of the charging. The way the coffee beans break, that largely determines what the charge is. And this makes a lot of sense, that because darker roasts they're more brittle, so they're more likely to fracture. And this is probably why they get a lot of charge. Now for the next part of the study, which has gained the most attention, which is the effect of RDT. What the authors did was they used different amounts of water for RDT. And what they found was that as you increase the amount of water, so as you go from 5 microliter per gram to 20 microliter per gram, the amount of charge reduces. And by the time you reach 20 microliter per gram, the net charge is 0. With RDT, what they found is that the number of aggregates is smaller. So aggregates which are formed by the fines sticking to the boulders is significantly reduced. And interestingly, they found that you can achieve the same effect with just a small amount of water. So just with 5 microliter per gram, you can make a big difference to the extraction of the coffee. Now, whether this is actually true, you will find out more in our experiments. Now, what about the effect of RDT on charge? Now, charge itself dissipates quite quickly. So if you leave the coffee, if you just don't do anything to it, you will find that the charge dissipates fairly quickly. So in another study by Professor Hendon, what they found that it takes roughly about 100 seconds for light roast coffee and about 200 to 300 seconds for dark roast coffee for the charge to go away completely. What this means is by the time you've done WDT and then you brew the coffee, the net charge is almost near 0. The problem is that all the aggregates which are formed, they are formed within the grinder itself. So by the time the grounds are coming out of the chute, you already have all these aggregates, and the net charge of these aggregates is going to be 0, which means when you use things like ionizers to deionize the coffee, that's not going to have any effect on the aggregates. And now for the most controversial bit of the experiments, the effect of RDT on extraction times. Now in this study, what they did was they used a medium roast coffee, and they looked at how long it takes for the coffee to extract with and without RDT. And what they found was quite surprising, that the extraction times were increased by about 50%. It also took a longer time for the flow rate to become stable. And what they reckon is because you don't get a lot of aggregates, the average particle size is of course smaller. And this is why you get better extraction from the coffee. But these results were not replicable. So James Hoffman and Lance Hendrick, they have done extensive experimentation on coffees, and they found that the results were quite variable. Lance, of course, has done a lot of study on the niche zero. So in this video, I'm going to talk about my experiments, and what I found was really surprising. If you like the video so far, please don't forget to subscribe. It is really important for the channel to increase its visibility. So for these experiments, I used one medium dark roast coffee, one medium coffee, and a light roast coffee. I used the 078S grinder and I've set it up at 1100 RPM. And for the spray, I used this spray. It gives about 40 microliter per spray. I use about 15 grams of coffee, spread it in a tray, and then spray it. For 20 microliter per gram, I used about 7 sprays, which is about 280 microliter. And for 5 microliter per gram, I used 2 sprays, which is 80 microliter. Now, typically after grinding the coffee, my standard technique is to do WDT in the container for up to a minute, and I also puck rake. The first coffee that I tested was a medium dark roast coffee. Typically, I use 2-bar pre-infusion for about 10 seconds or so, turn the paddle until the water debit is about 4 ml per second. I then look for a pressure of about 8 to 9 bar. I try and maintain the flow at about 2 to 2.5 ml per second. Typically, I'm looking for a ratio of about 1:2.5. With 20 microliter per gram, I found that the extraction times were slightly prolonged. I thought the coffee tasted a little bit better. I thought it was a bit smoother, a little bit less astringency. But the extraction times were not markedly prolonged. But if you look at Chris Hendon's study, they found that the extraction time was prolonged by up to 50%. Now, why is this the case? So I thought a bit more about it, and then I realized that the study has missed out an important variable, and that is the WDT, the Wise Distribution Technique. Nowhere in the study do they make any mention of WDT, and we know that WDT can actually have a big impact on extraction times. So naively, I thought perhaps if you're doing RDT, then you get less aggregates, which means maybe you don't actually need to do WDT. So this was my hypothesis, and my hypothesis was completely wrong. Simply doing RDT and not doing WDT, it actually reduced the extraction times, and the coffee which came out tasted terrible. So my next test was with 5 microgram per liter, and it did something that I really did not expect. Now, according to the Chris Hendon study, even using 5 microliter per gram, you should see less aggregates. So I was expecting that the coffee that came out would be more flavorsome. But using a small amount of water, 5 microliter per gram, it actually had a detrimental effect. The extraction times were really fast, and the coffee did not taste pleasant. Somehow, adding less water seems to be detrimental to extraction. The next coffee that I tested was a medium roast coffee from Colombia, a Colombian Antioquia. For medium roast and light roast, my technique is similar. So I use pre-infusion of up to 15 seconds of up to about 4 bar. And I turn the paddle to a water debit of 4 ml per second. Again, I'm looking for a pressure of about 8 bar and a brew ratio of 1:2.5. I maintain the flow rate at about 2 to 2.5 ml per second. With 20 microliter per gram, I found that there was again a slight increase in extraction times. I think it did not actually improve the flavors. If anything, I've preferred the coffee without the RDT. And just like with dark roast, I found that adding a small amount of water, 5 microliter per gram, it reduced the extraction time, not as much as the dark roast. The extraction was faster, and the coffee that came out, it tasted okay. It just wasn't as complex. Tested again, and again I got the same results. So I thought the next step would be to test with even more water. So I tested at 30 microliter per gram. and the extraction time was even more prolonged. Again, the flavors were not that great. I prefer the coffee without the RDT. So I increased the water content again to 40 microliter per gram. And this time I found that the effects were completely the opposite. The extraction times were even faster. This is not surprising because in another study by Professor Hendon, he showed that beyond a certain point, and for his EK43 that was I think 50 microliter per gram, too much water actually meant that particle size started becoming bigger again. This indicates activation of some other process, that is the wet or capillary aggregation process. The next coffee was light roast coffee, and the results were even stranger. Remember that with light roasts, they are either neutral or the net charge is positive. With 5 microliter per gram, I found reduction in extraction times and a faster flow rate. The flavor was not bad. It just wasn't as complex. I was going to test with 20 microliter per gram, so I sprayed the coffee beans, but then I was distracted. So I had a phone call, and I think I'd left the coffee beans for about 5 or 10 minutes or so. And when I came back and tested the coffee, to my surprise, the extraction was really fast. Even almost as fast as the 5 microliter per gram. So what's going on? So what I did was I tested again with 20 microliter per gram, but this time I ground the coffee immediately. And I found that the extraction time was still a little bit kind of fast, but not as fast by just leaving the beans. I actually did not enjoy the flavors of the extraction. So what have we found out so far? That with 5 microliter per gram, it results in faster extraction for all roasts, and it gives less complexity. 20 microliter per gram results in slower extractions for medium and dark roasts, but slightly faster for light roasts. It perhaps improves the flavor for dark roasts, equivocal for medium, and diminishes the flavor of light roasts. So with any of these values, whether 5 microliter or 20 microliter, I did not get any great extractions. And then I remembered Lance Hedrick's video. In his video, he found that he got the best results from the niche with 10 microliter per gram. He found that with 10 microliter per gram, the extraction times were similar. So I tested the 10 microliter per gram on the medium roast. The extraction times were similar, but this was achieved at a lower pressure of a maximum of 6 bar as compared to 8 bar without the RDT. The flavor was more complex, but with less body. I then tested the light roast, but this time I used an even smaller amount. I used 2 microliter per gram. The extraction was somewhat faster, with a flow rate of about 3 ml per second, and the maximum pressure was 6 bar. The flavors, however, were much, much better. There was more clarity, and the coffee that I used, it promised bright flavors, and this is exactly what I got. Next, I did some testing with the medium roast again, in that I sprayed the beans with 20 microliter per gram, left it for 5-10 minutes, and I got the same results as the light roast. The extraction times were really fast, and the coffee tasted awful. Then I did some testing with the niche. Now Lance Hendrick has done a lot of testing on the niche, so I don't think I need to replicate all those tests. So I tested a medium dark roast coffee with 5 microliter per gram. The extraction times were similar, and what I found was with the niche, with the 5 microliter per gram, it actually improved flavors. The coffee tasted more complex, and there was a bit more clarity than what I would expect from the niche. So what can we deduce from all of this? It is crystal clear that for every grinder, for every burr, and for every coffee, there is an optimal amount of water that you need to use for RDT. Using too little or too much is going to have a detrimental effect on your extraction and your flavors. For the 078S and for the coffees that I used, for dark roast, the optimum amount was 20 microliter per gram. For medium roast, it was 10 microliter per gram. And for light roast, it was 2 microliter per gram. Now, why RDT plus WDT, it results in slower extraction as compared to RDT alone? That's very easy to explain. RDT results in smaller grind size and WDT results in better distribution. But why using just small amounts of water results in faster flow rates, I cannot explain, but I have a theory. I think the effects of the RDT, they depend on the water on the surface of the coffee beans. So somehow the water on the surface of the coffee bean, it influences the way in which the coffee bean fractures. Somehow it interacts with the interaction between the coffee bean and the burr. Once it is absorbed in the coffee, it actually has a detrimental effect on the extraction. This is just a speculation. I have nothing to support this claim. It's simply based on my experiments. There are a few things that you need to be aware of. When you are doing the RDT, especially in the 078S, the beans get stuck in the hopper. And what I found is that if you realize afterwards that some of the beans are stuck in, and you then grind them, I found that you get an inconsistent grind. And the extraction was always fast and the coffee never tasted pleasant. So RDT does make a difference. It does improve things, but it is one other variable that you can get wrong. Remember that with the 078S, you can get great results even without RDT. But if you want to push that extraction a little bit further, if you want to get that little bit more flavor, then RDT will definitely improve things. This is, of course, a small sample. Please feel free to add your comments, and if you like this video, please don't forget to subscribe.